Alrighty, y'all, are you ready to learn? Today we're taking a look at the recitation for April 20th. And for this one, we're going to start looking at torque and various forms of equilibrium. Right? So our first question, right? We have a balance scale with a meter stick and a mass. Right? Same way we have like a triple beam balance, but we just have one beam for this one. Right? We attach some unknown mass on this side, and we have a known that this is 1 kilogram that we can move in various points over here. So I'm going to draw an extended force diagram. This means I can't just draw a dot and say, wow, what a lovely picture of a meter stick. This time I have to actually pretend to draw the meter stick. Right? What a lovely meter stick. Right? So we have on one end our unknown mg, right? Our force from our unknown mass. And on the other end, we have, somewhere over here, I could just put it wherever because I can move it around later. But that's going to be our 1 kilogram mass. So for this one, m is just 1, so this is just going to be g. But remember, this is multiplied by 1 kilogram. So it's not just g. It is still m times g because it's a force on a force diagram, but it equates out to just g. Right? But this isn't fully together just yet because we still have the support that's holding it up. Right? Because if I'm drawing my force diagram, I draw a circle around the thing I'm drawing a diagram of, cut off anything that the circle intersects with, and make that a force. So we still have to find in the center, right there, some force from the pivot holding it up. Right? Cool. Here's our force diagram. And now we need to choose a pivot point. Right? So we choose a pivot based on locations of forces that we don't know and we don't care about. Well, that's pretty obvious. I already said this is the one we're trying to find. This is the one we know. And this force in the middle I just labeled as an F because I don't know what it is, but I don't really care what it is. So that's going to be our pivot point, right? Because that'll just get rid of this force when we start looking at torques. Not get rid of it, but it'll make the torque from this force 0 about this point. Therefore, we can just kind of ignore it and look at everything else. Right? We don't know it and we don't care about it. So there's our pivot right in the center of our thing. Right? And now we know our system is balanced when we put the mass in a certain place. So I'm going to move our picture down. And we know that, a little bit more space, that this force here is going to be 20 centimeters away from here, or 0.2 meters. And this is in the center, so this is going to be 50 centimeters or 0.5 meters. Right, meaning this little distance in the middle is 0.3, just to get our dimensions all worked out. Right? So we have to figure out what the unknown mass is. We have to solve for this m. So now we say our Newton's second law for rotation, right? Our sum of our torques has to equal 0. So now we think about what torque is doing what. So we have a torque, a force, times a radius, right? And we want the perpendicular radius, and since this is going to be perpendicular to our meter stick, we can just use this 0.5 meters. So we have our torque from that, our mg times 0.5. Right, there's our torque from that one. And we're going to add our g, right, because this is our 1 kilogram times g, times the 0.3. So g times 0.3, and that just has to equal 0. Oh no, problem. I don't know if you've noticed, but two positive numbers, the way I've written it, they're both positive right now, can't equal 0. So we have to think about now whether or not our which one's positive and which one's negative, whether our torques are positive or positive and negative, whatever they are, right? So our convention is that counterclockwise, meaning going this way around a circle or around a pivot, is positive, right? So let's think about which one goes which way around our pivot. Here's our pivot here. If I were to look at this, if I were trying to rotate this around from this force, if I held it stationary here and just applied this force, that would cause the thing to rotate this way. If I keep drawing that circle, we can see that's clockwise, meaning this is going to be negative torque. And now if I do the same thing looking over here, here's our pivot, here's our force, right? I hold this stationary, see how it would rotate. It's going to rotate counterclockwise, meaning that stays positive, right? And really what I'm saying, I'll look up here, but, right? Holding this force, just looking at what this force is doing, if I take this, hold the center stationary, I rotate it based on that force, it goes around clockwise. On this side, based on this force, holding the pivot stationary, it would rotate counterclockwise. And that's really all we're envisioning when we do this, right? To figure out if it's positive or negative for this case. And now we're modifying our meter stick. So we have to, because we want to measure a mass that's more than 1 kilogram. So we shift the rod to support it at the 80 centimeter mark. So now we have to draw a new force diagram. So I'm just going to steal our old one, like I did before, but I'm going to shift this pivot point over to our 80 centimeter mark. I'm shifting where the pivot is acting, right? Because that's what it says. That force is that represents the pivot pushing, holding the thing up. That's going to be 20 centimeters from this side, or 0.2 meters, right? Because it's 80 centimeters from the left, right? So here's our new extended force diagram. Right? But it's not quite complete just yet, right? I left it out before. Again, I probably shouldn't have. This isn't a complete force diagram either. But we also have the weight of the thing, right? I always say, draw your circle, add the forces based on what's doing what, and then also gravity is acting on it because we're on Earth, so we have gravity to think about. But gravity always acts at the center of mass of the thing, right? And for our meter stick, that's going to be in the center, right where we said our pivot was. So we already ignored that, right? So that's technically, I shouldn't have ignored it before, but it disappeared because of how we chose our pivot. Now, can't really ignore that. Because if we're talking about forces we don't care about, forces we don't want to measure, we should keep the pivot above we should keep our pivot point above that support. Because we don't know this force and we don't really care about that. We can measure the mass of the meter stick pretty easily and just apply it here. But we can't really measure that particularly easy right now. So we'll just ignore that and it'll be fine. That's actually, I'm skipping ahead a little bit. You won't get precise measurements unless you consider the mass. Why does it matter when the support is attached at 50 centimeters, but why does it not matter when it's attached to 50 centimeters, but it does at 80? It has to do with how we're selecting our pivot, right? Here, our center of mass is above our support, so it disappears with our support force disappears. But in this case, it's not, we moved our support, but we can't move the center of mass. So we're going to put our pivot above the support, which we don't care about, but we do have to consider that. That being said, it's going to make it a little not precise, but we're not going to be doing any math with that just yet until we get to the next part. But I just skipped ahead a little bit. And now we have to just decide, why can we measure heavier masses than if we attached it at 50 centimeters. Well, this comes back to, right, we can balance forces, right? The way we used to say, we would say sum of the forces in the x, sum of the forces in the y. But now we can also balance torques. So the sum of our torques has to equal 0. So whatever torque this has, this mass, so our mg times our new radius, which is 0.2, right? Just ignoring that, that's going clockwise, so that's negative. But either way, our radius for this is going to be shorter than our radius for this, like our maximum radius for this. Therefore, this, even though it just weighs 1 kilogram, even though it just has a mass of 1 kilogram, it could still apply the same amount of torque as something that had a greater mass because it's going to have this greater radius. That's kind of tricky. But, right, since we're saying, right, our torque is our radius times our force. So our radius times our force. Even if this force is greater than this force, we have the radius that's gonna change based on that. That's our variable, really. We have mg and 0.2 plus our, again, just ignoring the center mass for right now, times whatever this radius is, has to equal 0. If, say, we know that this is our, what did we say it was? Oh, I didn't finish solving out the problem. My bad. But yes, we got our positives and negatives. One equation, one unknown. I'm going to divide by g through everything. Add this to both sides. Then we're going to get that. Fully just didn't finish solving that. That was my bad. M equals 0.3 over 0.5, which makes it 0.6 kilograms. Right? There we go. Great. Wonderful. There's your answer to that. It's my bad. Say we know the mass of this now because we measured it somewhere else. Now our only variable is this radius, because again, they have to stay equal. Our torques have to stay equal. We're not changing this mass, we're not changing this mass. Obviously, we're not changing gravity, and we're not changing this radius. So the thing that changes, again, it's a sliding mass. The thing that changes is the radius. So that's going to be accounting for, because we can have a larger radius, we can have a larger torque, which can match a larger force. Cool. Next problem. Sorry I mixed that one up a little bit, but keep trucking along, right? So we have a 4-meter long pole and extends out from the side of a building. We have this angle theta, 60 degrees above our horizontal. We have a sign hanging from the pole with a given mass. We know the pole has a given mass. And now let's draw ourselves a force diagram, right? Well, that's what the first question is, but so here's our pole. Just drew it a little thicker so we can see what it is. And now we think about what forces are acting on it. So let's draw. I always draw my circle around what I'm looking at and cut anything that goes through it. Ooh, I did not draw that very well though. Right. So we have the cable here applying a tension from that cable, and we know that that cable is horizontal, right? So we know that direction. We have a sign here also applying a tension, and that's going to be 1 meter from the end. I'm going to call that TS. We know that's 1 meter from the end. Yeah, that's just the tension from the sign, and again, we know that's hanging vertically. Then we also have something going on this end. I don't know what it is. I don't know what direction it's in. It could have a Y component. It could have an X component. I'm just going to kind of do that for right now. We'll figure that out in a hot minute. And then we also have to consider gravity, right? So it's a uniform pole, so our center of gravity is going to be halfway up, which is which is our 2 meters, right? Half of a 4-foot pole is 4 foot. 4 meter pole is 2 meters. Okay, there we go. Here's our force diagram with some dimensions, just some extra information that we don't really need right now, but it's just important to keep in mind where things are going. Now we have to choose our pivot, right? So this is where we get to say, what do we not care about? What do we want? What do we not know? What do we not want to know? What are we trying to find out, right? So eventually, we don't know, well, we know the mass of the sign, so we can get the force in our sign, from our sign. We know the mass of the pole, we can get this. We don't know the tension in the cable. We could probably find that pretty easily. But we don't know the magnitude or the direction of this force down here. So I'm going to plonk my pivot down here, because no matter what direction this is facing, it's always just going to be pointing at this pivot. Therefore, the torque's going to be 0 from whatever's going on down here. So we can just ignore that, right? Which gives us a lovely equation to figure out our other things, right? So now we were given this lovely chart down here where we get to calculate the torque for every force. So our various forces, we have gravity, we have our tension from the sign, we have our tension from the cable, and we have whatever's going on at the wall, the reaction from the wall that just keeps this thing from moving, right? Because if we do want to do a sum of the forces, we could say sum of the forces in the x, sum of the forces in the y, or x and y would equal 0. We could solve for these, but we don't have to, right? Because we can just put a pivot there and ignore them for right now, right? So our distance to pivot, well, we know for sure that this one is 0. Right? So let's think about the other distances to our pivot. I kind of labeled some of them already. Our gravity, that's 2 meters. So you can put that here. The tension from the sign is 1 meter away from the end, meaning it's 3 meters away from the pivot. There's that. And our tension from the cable was just on the other end of the pole, so that's going to be the 4 meters of the full length of the pole. And size of the force, right? mg, how much, let's check the mass. The mass of the pole was 80 kilograms, and the mass of the sign was 50 kilograms. So our mg is going to be 80 times g, and this is going to be 50 times g, right? And then our tension in the cable, that's what we're trying to figure out right now, so that's just going to be Tc. Actually, no, I'll just call it T for ease. Okay? And size of the force, we don't know this, and I don't really care right now. We'll just put that as a question mark. Because again, I don't really care. No, we're not even figuring it out. Goodbye. We just don't need that. Okay. We don't need that because there's no angle between it because it's just pointing straight at it. We don't care if it's positive or negative, and it doesn't have any torque because, right, it has a 0 radius. Multiplying by 0 gives us 0. So I won't put an X there, actually. I'll just put a 0. There we go. But now let's get the information for everything else. So our theta, angle between our force and our radius. So let's start with gravity, right? Go down our radius. Let me go this way. We know that this angle here is 60 degrees. So here's our radius, here's our force, angle between is going to be there. Well, if I were to imagine this like a right triangle, 60, 90, that makes this one 30 degrees. Right. So that is 30 degrees there, which is going to end up being the same for this one, right? Because this one's pointing straight down, this one's pointing straight down. We just get to say they're both 30 without doing any extra math. But I love math, you say, and I agree with you. Math is wonderful. It's so fantastic. We all love it. Now let's get the angle with our cable, right? This one, going back to our geometry, right? We have this line, our horizontal here. We know this is going horizontal. This is just one line cutting between them. So this is opposite interior angles. So that means that this angle and this angle are going to be the same, meaning that our angle here is going to be 60 degrees, and that's our angle between our radius and our force. So this one is going to be 60 degrees. Okay. Oh, we're supposed to take the sine of theta. This is just theta. We can just put a sign there. And I'll punch it into a calculator afterwards and say, wow, isn't it great? Now we get to figure out positive or negative. This is just whether it spins clockwise or counterclockwise, right? So if I look at, I'm gonna get rid of this real quick, just so I have some room. Now if I'm looking at what's doing what, I'm gonna start by looking at, let's start with gravity, right? Because that's where we started over here. Ignoring all the other forces, holding my pivot point steady. That would rotate around like that, like this way. And that would be, I forgot which way was which. That way is clockwise. So mg is going to be negative torque, right? And now we do the same thing. We look at for our tension from the sine, hold our pivot point steady, follow that force. That is also going to be going around clockwise. Therefore, you can say this is negative as well. Now we look at our tension from the cable, going around like this. That's going to be counterclockwise. Therefore, this one's going to be positive. Right? And punching all this mess into a calculator, right? We do size of the force, right? We do magnitude of the force times the distance of the pivot times the sine of the angle between them, and positive or negative, and that's going to give us a negative 784.8. This is a negative 735.75. And this, we can't just punch into a calculator because we still have this unknown. So that's going to give us 4t sine of 60. Okay, wonderful. And again, that stays positive. Cool, great, fantastic. Right? Now we just get our tension in the cable. Same thing we do. Newton's laws, no crime around here. Our sum of our torques has to equal 0. So if I take all of our torques and sum them together, well, adding 0 is just going to doesn't matter, but that plus that plus that has to equal 0. Wonderful, great, fantastic. That makes it so easy to now just do math, because this is one equation, one unknown. Math, my favorite. I'm so glad to see you again. All right, gives us, bumping it to the other side, 4t sine 60 is going to equal, what was that, 1520.55? And then just divide both sides, and that gives us our tension in the cable to be 438.9449759 newtons. Units are important. Always remember to add units, because otherwise this could be pounds, slugs, who knows? You know, fun fact, slugs is an actual unit of measurement. That was not just me listing the animal. Those of us that know, I'm proud of you. Those of us that didn't know, surprise. The American unit system is terrible. That's why we use metric. Now, we want to attach the cable to a different point in order to minimize tension. So what angle between the cable and the horizontal would support the pole with minimum tension? So I'm going to steal our force diagram again, and let's figure this out. How do we get a minimum tension? So you have to figure out what we can change and what we can't change. We still don't know these reactions, and I still don't care about them, so I'm going to keep my pivot down here, right? So we can't change the angle between this and the horizontal. Gravity is just going to be pulling straight down. We can't change this angle. The sine's still going to be pulling straight down. We can't change the magnitude of either of these forces because our masses are remaining constant of both the pole and the sine. So the only thing we can change is we're trying to minimize tension. and we're trying to find the angle at which to do it. So those are our two things we can change, meaning the same way when we had like some function of x and y, and we were trying to minimize y or maximize y, we just think about changing x in order to do so. So changing our theta to minimize this. So let's figure out how they relate. All right, so if I steal this from up here, instead of sine 60, this is going to be sine theta. And now we get to figure out how to make this a minimum. Well, if we're keeping this constant, if we're decreasing this, and this remains constant, that means this has to increase. So sine of theta, for tension to be at a minimum, sine theta has to be at a maximum. Well, what's our maximum sine theta? Sine theta, it's our whatever fun favorite function that looks wavy and cool and does a lot of fun things, and we love sine and cosines. Sinusoidal functions are our favorite, right? So our maximum is our amplitude, right? Which is 1. So the maximum that sine theta can be is 1. So what theta gives us sine theta equals 1? Well, isn't that super wonderful? But it's 90 degrees. Wow, isn't that great? Remember our unit circle? Right, here's our 0. Here's our 90 degrees, or pi over 2 if you're feeling spicy. Right? There we go. We have to remember what's the question asking. The angle between the cable and the horizontal. What I just figured out, I figured out sine this theta here. Means it has to be 90 degrees. That doesn't mean it's 90 degrees from the horizontal, because these are 90 degrees from the horizontal, and they're only 30 degrees from our radius. So this theta is our angle between our radius and our force, meaning that this has to rotate, right? Our 90 degrees has to be here. So if I draw in the horizontal to find that angle, we still have a horizontal here and here. This is still 60, but our angle between this and the horizontal is going to be 30 degrees. Okay? So that's how we minimize our tension. We maximize sine theta. Okay? And that's just the thing. If we're trying to minimize tension, it's always going to be a 90 degrees because we want sine theta to equal 1. Okay? But we have to remember that's between the radius and the force, but we're being asked for between the horizontal and the force. Okay? All right. Our dynamic equilibrium now. This is a fun one, though they're all fun because physics is fun. We love physics. So we have a unicyclist riding at a constant speed, 5 meters per second. The unicycle and her both have a combined mass, 70 kilograms, and the wheel of the unicycle has a radius. Let's get that real quick. 0.5 meters before we forget, right? Everything else we want to just keep in base units. And at that speed, we have a given air resistance, 80 newtons. That's fun and exciting. Now we have to figure out our angular velocity of the wheel. So, what we have a wheel. Ooh, that is quite the wheel. You know what? I'm going to make... Wow, I'm so good at drawing circles. All right, so here's our center and our radius. 0.5 meters, right? 50 centimeters, 0.5 meters. So exciting. There's our radius. And we know that altogether our unicycle is traveling at a constant speed, 5 meters per second. Meaning that as this thing's going forward 5 meters per second, our center of our circle, meaning our entire wheel is traveling like that. Relative to it, this thing is traveling backwards. Right, that's our rotational bit, right? So we're rolling without slipping, meaning that our velocity equals our omega, right? Remember, this isn't a W, it's omega. This is our angular velocity. This is our linear velocity. And this is our radius of our circle, right? So we get to say that omega equals v over r, right? Just dividing both sides by r. And that's going to equal, our velocity was 5 meters per second over our 0.5 meters. And that equals 10 radians per second, right? Units, very important, because this is an angular velocity now, and our angular everything is radians. And since it's a rate, it's a velocity, radians per second. Wonderful, great, fantastic. Love things going in circles. Now, we have to figure out the force of static friction that is propelling ourselves forward. So I'm going to draw a little picture. We have we're riding on a unicycle, and this leg is on that side, and that one's on that side, and wonderful, right? So we have our static friction pushing us forward. We also have our air resistance pushing us back. We know this is 80 newtons. And I know we've been doing so much with torque today, but we do get to go back to our friend linear Newton's second law instead of rotational, right? We're going at a constant speed, 5 meters per second. We're not accelerating, right? Constant speed, acceleration equals 0. So I can say the sum of my forces in the x direction equals, I'll call this Fs, right? I have to pick a positive and pick a negative, positive, negative, right? So Fs minus 80 has to equal ma, which is just 0, meaning that our Fs equals 80 newtons. Again, units, best friend, super important. So there's our force from static friction, right? We've been doing so much with torque, we almost forgot that that is a thing that we can do. However, it still is wonderful, great, because constant speed, acceleration is 0. So exciting. Now, we get to figure out what torque we get to apply to the wheel to maintain the speed, right? So, before I drew my whole picture of all of the person and the unicycle, now we're just going to be looking at the wheel, the unicycle. I'm so good at drawing circles. It's really amazing. And I'm so good at bonking the center on them. Okay, but we have to figure out what torque must she apply to maintain the speed, right? So we know that our wheel has some force, and I'm drawing this. I'm trying to draw it like tangent, but that's our force from our static friction. And if we're ignoring like the pedals, because the pedals are just going to attach here and make it spin, right? That's going to be some kind of torque applied. So I'm going to draw this. I'm going to try to eyeball what's going on. So if this causes it to rotate like this, we need a torque to, so it's going to go like this, right? And again, I'm thinking our net torque on the wheel. Since we have no linear acceleration, right, we have no angular acceleration for this, right? Remember our alpha. The same way we can say that v equals r omega, we can say that a equals r alpha. And since our acceleration is 0, our angular acceleration is also 0, meaning that our sum of all of our torques equals 0. And that's what I was just eyeballing. You don't have to worry about which direction you draw it in. I just wanted to, for the sake of demonstrating. But, right, we say our sum of our torques equals 0. This is going to cause us to rotate counterclockwise, meaning in order to oppose that, something has to be applied clockwise. If I ignore that fact and just write it as is, it'll spit out a positive number, or it should spit out a negative number. So if I ignore that we think it's going to be positive, I'm going to say the sum of the torques is going to be, right, and since this, we have our force from friction and our radius, and they're perpendicular, meaning our sine of our angle is just 1. So you can just say that force from static friction times our radius, which was 0.5. Ignoring that I think it's going to be negative, we're just going to say plus that t has to equal 0. Right? Our sum of our torques, torque from this, and the torque that we're applying, meaning that if we plug in our 80 newtons here, bonk it to the other side, you get that T equals negative 40 Newton meters, right? Which would give us the same answer as if I assumed that this was negative first. If I decided to say, I think this is going to be negative, therefore I'm going to say that Fs times 0.5 minus T equals 0. Now the answer I get is going to be 40 Newton meters. But since I assumed it was negative at the beginning, this 40 is acting in the negative direction. So that gives us just a 40 meters going around like that, 40 Newton meters going around like that. And this one just means the same exact thing. Negative, opposite the positive direction. Cool. All right, so thank you so very much for watching. I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this or anything else you want me to try to explain, and I'll do my best to try to explain it because I guess Sydney explains stuff.